I will begin with a, a word of prayer. Dear Father, we thank you for this morning. Thank you for these students and this time we have, and just ask that you be glorified in what we do this day, Lord. In your name I pray. Amen. So there's definitely time for your homework questions, but I think it's wisest for me just to put the additional examples at the start for the convenience of those who are not here, as opposed to, eventually we do more Gaussian elimination at the minute, I don't remember what mark, So, but so let's just do a few examples of Gaussian elimination. Well, it's not even exactly Gaussian elimination I'm doing at the moment. Actually, I'm just showing how to calculate the reduced row echelon form of a matrix. I don't even care for the moment what system it's attached to. I just want to be kind of start with a matrix and let's just try to do it. So let's see here. Suppose I had 0, 0, 1, 3, 0, 0, 2, 6, 1, 1. I'm reading column by column right now, guys. If you're not looking at it, you should, because I usually, my default is to read row by row, right? But when I'm making these up, it's convenient for me to do column by column for various reasons. And let's see here. And then I'll do 1, 1, 3, 4, and 10. All right, so let's call this thing M for matrix. And let's calculate its reduced row echelon form. So the first thing with this one is this one requires an opening move, which is not like what we did in class, right? Because we have to, so let me tell you some things that are kind of overarching guidance for this. This will have, it has E1, E2, ek as pivot columns, where those are the standard basis. So like after the row reduction's done, your pivot columns will be standard basis. There can be ones with zeros below and zeros above. So to start with, this 1 is in the wrong spot. Or you could say this 3 is in the wrong spot. I like the 1. So I'm going to put, first move, we're going to do row 1 swapping with row 3. That's one of my elementary row operations, right? What did we say? I forget which type that was. You guys remember? Type 1? Good. I will forget that. I already forgot it. So 0, 0, 1, 1. 0, 0, 1, 1, I guess. Yeah. And then the the fourth row, 3, 6, 1, 10. All right, now we've got, at least we got the 1 in the right pivot position. So identify, my first pivot. And what I want to do is I want to clear out any non-zero entries below that pivot. There's only one that I need to clear out, right? I want to clear that out, remove this, right? That's the goal. So how do I do that?
Row 4 minus 3 times row 1.
Right, and that's the right way to write it in my notation. The one which comes first is the one we're modifying. So when I write row 4 minus 3 row 1, that tells me I'm modifying row 4. The one case where this is not really the notation is the switcheroo. The switching, both things are modified, right? I mean, that's an exception. But multiplication by a non-zero scalar and this one, what are those, type what and what? What did you guys tell me the switch was? Type what? Type 1. So type 2 and type 3, we write the modified row first. Okay, that's my notation. And I use the arrows. If you look at my notes, I've got some that have tildes on them, right? And those are my brother's fault. No, I mean, they're my brother's contribution. I just cut and pasted some of his notes. He's got like a little handout on Gaussian elimination, which I've integrated into my notes because it's good. It's a good discussion, and he has nice examples. And you might even prefer his notation to mine. I don't know. Okay, so we subtract 3 times row 1 from row 4. That zeroes out this. It removes the 3. What about the 6? Oh, that also is gone, yeah. And then how about this? Minus 2, right? And minus 2, okay. Then, okay, at this point, we've finished clearing out under the first pivot. The first pivot's been cleared out. Now we have to identify our second pivot. So what you do, okay, so to identify the second pivot, we look for next non-zero column, right? Well, but non-zero, to be more specific, under the already existing pivot. So in my notes, the way my brother communicates this is he says you forget about the first row, and then you look at what's left and try to find the next pivot with that. So he makes this like he makes this gray if you look at my notes and his notation at this point. So we look at what's below the first row then. What do we got? We can't use the second. That's just zeros, right? So the next is the third column. And so what we do, remember, ultimate goal is to have E1, E2 as pivots. So this one right here is going to ultimately lead to an E2. We'll use that as our second pivot. All right, so my second pivot is that 1 and currently in the 2, 3 spot. Now I want to clear out, I need to remove 2 things with that 1, right? In the forward pass, I clear out, we're doing the forward pass right now. Forward pass identifies the pivots and clears out any non-zero things below the 1, the leading entry. So we want to get rid of this, and we want to get rid of that. There's no harm in doing 2 things at once in this sense. So we can do row 3 minus row 2. And in the same file swoop, we can do row 4. What? How do you get rid of that minus 2? Yeah, 2 times row 2. Very good. And what will that give us? So everything, let's see, what stays the same? Rows 1 and 2 stay the same, right? So we can just write those down. 1, 2, 1, 4. 0, 0, 1, 1, unaltered, right? And then by construction, we get zeros here, 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 and here, right? And what happens to the 3, 4 spot? We've got row 3 minus row 2. I think we also get a 0 here, right? And let's see here. And 0? Yeah. Okay, so let me put this into words. Every non-zero row has leading entry of 1 and zeros below that 1. Right? See this? Here's my 1 leading entry, zeros. Here's my other leading entry, zeros. This means the forward pass is done. Those are my pivots. This is what you might call the REF. This is not unique. If you did the operations a different way, you could get a different REF. At this point, all that's left is to clear out the entries above the pivots. So now we do the backwards pass, which is kind of very anticlimactic here. It's 1 step. So the 1 step would be row 1 minus row 2, right? Row 1 minus row 2, what does it do? It takes this 1, and it clears out this guy, right? It's going to annihilate that. And what are we left with? 1, 0. I'm reading column by column. 1, 0, 0, 0. 2. The second column is 2, 0, 0, 0. The third column is 0, 1, 0, 0. And how about the fourth? It's 3, right? 1, 0, 0. And there you go. This is the reduced row echelon form of M. Any questions?
You don't have to get rid of the 2 and the 3 because they're not above pivot columns, correct?
Not only you don't have to, you can't. You can't get rid of the 2 and the 3. See, because if you tried to get rid of the 3, what happens? If you tried to get rid of this 3, you subtract 3 times, 3 times row 2 from row 1. What would that do? That puts a minus 3 up here. But remember, the pivot columns, by definition, by part of the definition of Gaussian elimination, have to be standard basis elements. You'd be like, why? Well, essentially, this is part of the definition of what it means to be in the reduced row echelon form. Yes, you could do row operations to make it look different. Certainly you could, but that would not be the reduced row echelon form. Now, there's a proof in my notes, or at least a sketch of a proof, which shows that the reduced row echelon form is unique for a given matrix. And that's very reassuring because that means that we have a standard technique to find a sort of canonical solution to a given system, at least if it's over a field. Yeah. We'll do one more example of these, and I'll take your homework questions. Here, how about if we had something like A equals to, I don't know, 1, 2, 3, 3, let me make this a 2 actually. 2, 2, 3, 3, 1, 1, 7, 9, 10, 0, 1, 0, 1, 1, 1. There we go. This is a 5 by 3. I should probably do a smaller example, but I think it has to be big enough. I don't know. If you really want to see all of the nooks and crannies, just play with that website for a little bit, right? Just put in a big matrix and see how it goes. You'll get more if these examples aren't doing it for you. Okay, so I don't know. We got different ways we could go here. We could work with fractions, but I kind of, I really like this last. I really like this last row for the first pivot, right? So I think the first thing I'd do would just be to swap out row 5 for row 1, right? Because that would just make my life easier. Sorry, I seem to be writing it smaller now. Then what would I do? My first pivot would be the top spot, right? So I can clear these out. Row 2 minus 3, row 1. Row 3 minus 7, row 1. Row 5 minus 2, row 1, right? Row 2 is, okay, so we got 0. What we got here? Minus 2, minus 2. 2, 3. Row 4 is not changed. Let's see here. And then what do we got? 0, 0, and it's like a 1, right? I mean, probably the laziest thing to do here would be to bring the bottom two rows up to the second and third rows, because those are really nice. I'll do it a different way just to show you. So I would say we could also do this way, right? Maybe this will make it look like we're doing more. Row 2 divided by minus 2, right? Which would give me what? 1, 1, 1, 0, 1, 1, 0, 2, 3, 0, 1, 0, 0, 0, 1. And then my second pivot, right? My second pivot right here now. So I want to clear out these guys. So I do, what do? I do row 3 minus 2 row 2, right? And I do row 4 minus row 2. Right, what's my third pivot going to be? Should be E3, right? So that made my third pivot. I want to clear out the things below that, right? So let's see here. That looks like row, what we got? Row 4 plus row 3 and row 5 minus row 3. So in some sense, it's kind of like sweeping a room from side to side or something, right? I mean, as long as you keep sweeping the dust in kind of a systematic way, you always don't put dust where you already had it, you know? It's kind of like that, right? Sort of always like sweeping up and to the right, right? All the clutter. But we don't find a way to put all the numbers into a dustbin. The analogy's not really complete. It's kind of if you always just swept half of the room in a diagonal fashion and left the rest of it dirty or something, it's not really a very good analogy at all. But anyway, but you leave the dirt in a canonical way so we can all sweep the room and get to the same pile of dust no matter how we start. So, you know, that rescues my analogy. Not really. Whoa, I could not have planned that if I want. That was not on purpose that we ended up with ones like that from this. That is an accident. I just made this up, okay? That we all ended up with all ones like here. That's pretty cool. Now the backward pass is at least slightly exciting. So the backward pass goes like this. We start with the latest greatest pivot, in this case E3. And we want to clear those out. So clearing those out, what's that look like? That looks like row 1 minus row 3 and row 2 minus row 3. Which gives us what? 1, 1, 0, 0, 1, 0, 0, 0, 1. And the bottom two rows are zeros. There are some instructors who just don't write the rows of zeros at the bottom once they know there's rows of zeros. I am not one of those people, because then I would always be talking to you guys about where the zeros went. And that would not give me joy. So instead, I just take the time to write 6 zeros, which is not a large burden for me, for the lack of confusion of omitting the zeros. And then, so swept clear. At this point, this guy is E3. That's the finished product, right? And so I go back to here. There's only one to remove. So we got row 1 minus row 2. And this gives us a, this gives us a 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 0. And there you go. This is the reduced row echelon form of A. Any questions? Yep.
Would it also been okay, since it worked out this way, to have just said row 1 minus row 2, since that would have gone ahead and gotten rid of those row 1 minus row 2? And
Back here?
yes.
No, can't do that because you're modifying row 1 with row 3.
Right, but instead of modifying it with row 3, could you?
Oh, you're saying if you had instead done.
Yeah, just done it in 2 steps.
Yeah, sure.
So row 1 minus row 2.
That is true, and that's a good example of going off the algorithm, but being more logical. Right. So you're following the spirit of the algorithm by suggesting we replace this move with row 1 minus row 2, which would have zeroed out both of these ones. Fantastic. It's just that I didn't do that because I was trying to illustrate the backwards pass, which goes column. It starts with the last pivot and goes back. But it's actually much more important to me you understand the goal and the spirit of it as opposed to the precise algorithm. Because I think following the precise algorithm actually slows you down in the big picture of things. But if you need to, do it. Okay? All right. So it'd probably be useful for me to talk about what this means for the underlying equations, right? While we have this up here before I erase it. What system of equations would this M correspond to? If you want to think of M as being the augmented coefficient matrix, right? If this is A with B concatenated, what system of equations would this be? If I think about, the last column being the inhomogeneous column, it could be a system of equations in x, y, and z, right? So it's kind of a silly system, right? The first equation is z equals to 1. The second equation is z equals to 1. The third, so I think we can relatively safely figure out what z is in this system. The third equation would be x plus 2y plus z equals to 4. And the fourth equation was 3x plus 6y plus z equals to 10. Right? And what we learned is that this system, right, is equivalent to this guy up here, right? And what's this system look like? In terms of equations, what's this say? This says that x plus 2y plus 3z, x plus 2y equals what? Equals to 3. And you guessed it, z equals to 1, all right? So the non-pivot column provides parameter for solution set. So what's the non-pivot column here? Ignoring, okay, so here the last one is the inhomogeneous term. Let's say the non-pivot columns in the coefficient matrix part of the augmented matrix, okay, the first up to the last one. So it's y, right? The y is the non-pivot column. And so you see what we have x is equal to 3 minus 2y. Solution set, what is it? So I'll write it out generically. Well, let me just write it out. We got x is 3 minus 2y. Y is y. What's z? Z is equal to 1 in the solution set, right? So there it is. Y is a real number. Well, I didn't say. I said it's a real number, but you could just as well put y. I mean, this is ambiguous, right? Until I say otherwise. So, I said that I have to tell you what we're working in. This is, if I say over R, over the reals, then I should put real parameter, right? If I said over the rationals, then that real would be replaced with a Q, If I said, that would replace this with Q, right? You could also put a C in both places reasonably. Bless you. And does this make sense? Yes. Now here, what if I was to identify this as a system of equations, again with the last column being the inhomogeneous column? This is what? This is 5 equations and 2 unknowns then. So you got like 2x plus 2y equals to 3, 3x plus y equals to 1, 7x plus 9y equals to 10, y equals to 0, and x plus y equals to 1. Graphically, what is that? I mean, graphically, each one of those equations, we can visualize the solution set as lines in the plane, right? So if we had a solution set, if we had a simultaneous solution to all 5 of these, this would mean that those 5 lines intersected at some common point. Is that going to happen? Probably not, right? And that is apparent because if you look at the row equivalent matrix over here, what system of equations does this give you? This gives us what? Our first equation, x equal to 0, right? Our second equation, y equals to 0. Our third equation, 0 times x plus 0 times y is equal to 1. And then our last 2 equations are 0 equals 0 and 0 equals 0. True, but not particularly insightful. The third one, though, you see that's a problem, right? So something I'll be talking about in class Friday, guys, is the difference between consistent and inconsistent systems. Example 2 is an inconsistent system. The solution set is in fact empty. There is no solution. Which wouldn't be surprising if we actually graphed those 5 lines. You'd see that there is no common point. They've got different slopes and such, right? Now, that's not all you can do with these, but I'm going to leave it at that for here. So, you guys have questions about the homework? Yes, no, maybe so? Oh, it might be helpful for me to do an example of a system over like Z mod a finite field. Is there a question in the homework about that? I can't remember if that was in mission 2 or mission 1 where I put it. Have I asked you to solve any systems of equations where we're not working over the reals or rationals, we're working over like a finite field? No? Not in mission 1? Okay. Cool. So you guys have any particular questions? Yep.
Problem 13, you say define x as x, y, z, w.
Yeah.
And then you say the order the variables in order x, y, z, w.
Uh-huh.
What exactly do you mean by that? As in, like, define x. Are you looking for values there, or?
So, if I have, x plus y plus z equals to 2, and I say, x minus 2y plus 7z equals to 30, I don't know, whatever. But I say order variables y, x, z, I'd get a different coefficient matrix than I would if I said order them x, y, z. Here, I'll write both. So in the x, y, z order, it's what you would kind of already probably have figured out. 1, 1, 1, 2, 1, minus 2, 7, 20, 30, rather. Right? Versus if I order the variables like this, then I really should be thinking about writing the equations like this, right? So in this way, the augmented coefficient matrix would be 1, 1, 1, 2, minus 2, 1, 7, 30. There's an ambiguity that's always present, like how do you order the variables, right? Because unless you declare that ordering, augmented coefficient matrix in their isolation are not meaningful, right? So sometimes you'll see people write, like above this is the x, this is the y, this is the z, and this one, this is the y, this is the x, this is the z, if there's an ambiguity, especially in like applied problems. So that problem you're talking about, problem 13, I say that if you look at the matrix, x equals to x, y, z, w, I say you can find a corresponding system of equations in x, y, z, w. So if some of you decided to order the variables x, z, y, w, that would get a different matrix than if you did it x, y, z, w. So I wanted to declare the order so that the grader has a unique answer to look at. That's still not entirely accurate, right? Because if you look at what you're going to get, let me just kind of tell you what you're going to get. Here I'll just kind of sketch what you get. You get, so ax times xb, right? Equals to I, which is 1, 0, 0, 1, right? So you work that out. What happens? That works out to something like Pac-Man, Ghost, smiley face, dead face, equals to 1, 0, 0, 1, right? And so that's a matrix equation. It corresponds to 4 scalar equations. Those 4 scalar equations are Pac-Man equals to 1, Ghost equals to 0, smiley face equals to 0, and dead face equals to 1. But, you could just as well row swap, right? So if you order, depending on how you order those equations, you might get a different augmented coefficient matrix just the same. They'll be row equivalent, provided that you actually order the variables x, y, z, w as I asked you to. So it reduces the confusion at least the grader only has to look and say, oh, they just switched this row and that row, This is not a bad problem, by the way. Like, don't just skip it because it's got a bunch of words. That would be foolish. That's generally true of my homework. More words does not equal more difficulty necessarily. Yeah. There are exceptions, though. Other questions? Yeah.
For problems 14 and 15, can you just explain what exactly you mean by the geometry approach versus the algebraic approach?
No. So problem 14, I tell you, so in problem 14 and 50, inside the problem, I give you an algebraic characterization of a plane and then of a line, right? So, and I tell you that, if we have a plane ax plus by plus cz equal to d, then the normal of the plane is abc, right? I say, suppose the points 1, 2, 2, 2, 3, 3, 0, 0, 2 are on a given plane. Find possible normals for the given plane. So let me just do a couple of examples, make sure that we understand each other. So if I gave you that the normal was, if I gave you that ABC, was equal to 1, 2, 3, right? Then that would tell you that the equation of the plane looks something like what? X plus 2y plus 3z equals to d. So there's lots and lots and lots of planes with that normal, right? I mean, if I could picture it, roughly speaking, maybe the plane looks like this, and there's that 1, 2, 3 normal, right? But I can take the same, same plane, well, same direction, 1, 2, 3, and I can shift it over here, and I also have a plane with normal 1, 2, 3, but those are different planes. To be more, perhaps better. And it's hard to communicate these things without props. So here, this plane has a normal which points that direction. Like there's the face here, normal points that direction, right? If I move it over here, it's still pointing in the same direction, but these would be different planes. So in order to fix the plane, I also need to give you a point on the plane in this current setup, right? So you pick any point, what point you want. Just make up 3 numbers, it doesn't matter. 1, 2, 3. Anything but that. Anything but that. 2, 1, 7. Okay, sure. If that point's on the plane, what does it mean for a point to be on the plane? What is the plane? I mean, this plane is the set. It's the solution set, right? This is all x, y, z in R3 such that what? X plus 2y plus 3z equals to d. It's all the points in x. It's all the points in R3 which satisfy the equation of the plane. I mean, that's what the plane is. The plane is a solution set to a linear equation. 1 equation, 3 unknowns. So if the point 217 is on the plane, that removes this mysterious d from the. We can figure out what d should be in this problem, right? So like 217 is an element of my plane P. That implies what? That implies that that x, which is 2, all right, plus 2 times y, which is 1, plus 3 times z, which is 7, is equal to d. So d is not just some hypothetical constant. It's actually what? If the point 217 is on the plane. D is equal to 21 plus 2, 25. So let me summarize. There exists a unique plane, x, p, which is the solution set of x plus 2y plus 3z equals to 25. And this plane P, what is it? It has with normal 1, 2, 3 and point 217. So I mean, once you give me a normal and a point, there's a unique plane, right? Admittedly, the equation's not unique, right? I could take that equation and look at any row equivalent. I mean, I could multiply the equation by a non-zero scalar. I'd still have the same solution set, right? But anyway. Now your problem, what did I tell you? I said you got some plane, right? And you got 3 points. And I asked you to find what are possible normals. So here's a similar example. Suppose I had 3, 7, 7, I had 0, 1, 1, and I had 1, 2, 0. Suppose that these were all points on my plane, right? So graphically, that means that these 3 points, they're out there, right? Now in Calculus 3, I teach geometric ways to solve this problem using the cross product and such. But here, I don't want you to take that approach. I want you to take a linear algebraic approach, right? So what is the linear algebraic approach? Solve it as a problem of linear algebra, equations. So P, in other words, P, Q, and R have to be elements of the plane P, right? They have to do what? They have to solve AX plus BY plus CZ equals to D, right? For the appropriate choice of A, B, C, and D. And I told you the question asks you to find all possible A, B, C that make it so. Like, I can show you geometrically why there's going to be more than one answer. The thing is, if this ABC works as the normal, so does any scalar multiple of it, right? So there's not going to be one answer. There's going to be a whole infinite family of answers, right? And we're also going to need to insist that at least one of A, B, and C are non-zero. Did I put that in the problem? I should have, if I didn't. Because, of course, if you take A, B, and C to be, oh, wait a minute. Never mind.
You do say that on problem 15, but not on problem.
Yeah, I think I might need to say that here, too, because if I just put A, B, and C all 0, and I put D equal to 0, does it work? If you make this 0 equals to 0, do these 3 points solve 0 equals to 0? They do, but it's not a plane. It's just all of 3 dimensions. Are those points in 3-dimensional space? Yeah, they're there. Not really about a plane. Okay, so we should assume that at least one of, what I'm trying to say is when you look at the solution set, one of the possibilities will be A and B and C all 0. I should have removed that. I had the sense to remove it from the line problem, but I think I forgot to make a comment here. So what does that, getting to the point here, what does that mean? These points have to solve that. What's that tell you? What is a solution to a linear equation? It means you plug the thing in and it works, right? So specifically, that gives us what? 3a plus 7. We don't know a, b, c, so we have to leave them as variables, right? And in my problem, we have b plus c equal to d. We have a plus 2b equals to d. Do you care about D? You don't care about D, so you might as well eliminate it, right? Or you could use Gaussian elimination. Anyway, here you go. So you got to work this out. We've got, what, 3 equations? And how many unknowns? 4, right? It so happens that those equations are independent, so you're going to have one parameter in your solution set. Here, A, B, and C, and D are real variables. Do you want me to do it with Gaussian elimination? I can do it with Gaussian elimination if you'd like to see it, but no.
Why is it that we don't care what D is?
Well, that goes back to the question which was stated. The question asks you, what are possible normals to the plane? The normal is ABC. So D doesn't have anything to do with that, so we can eliminate D if we're looking for ABC, is my point.
Okay, so then you would just set it up as a 3 by 3 matrix?
No, I'm not saying you ignore D in that sense. I'm saying that when you're solving it, you can eliminate it. For example, if I was to use, not Gaussian elimination, but just direct methods, my opening move probably would be, B plus C is equal to D, right? But it's equal to A plus 2B, right? Which tells me what? That tells me actually that A plus B minus C is equal to 0. So I trade my last 2 equations for that nicer equation with no D. And the first two equations also give me an equation with no d. What do those give me? Those give me 7a plus 7b plus 7c equals to, well, equals to d, but equals to b plus c, right? So that translates into the nicer equation, 7a plus 6b plus 6c equals to 0. So if you look at star and you look at star star, that's much nicer. Now we've got two equations with three unknowns. There's no d, so and tell you what, I'll finish it off using Gaussian elimination. Let me use here a mixed method example. How about that? So let's see here. 1, 1, minus 1, 0. 7, 6, 6.
I think that 7a is supposed to be a 3a.
Oh, thank you. That would be most helpful. Thank you, thank you, thank you. Stop me from getting any further into this. 3, which then does what? That makes this a 3, which then makes that a 3, right? Do we agree? I mean, it's a simple matter to eliminate d by just by basically setting the equations equal, since they both agree on d. And that gives me this relatively simple, three unknowns, two equations problem, which I like Gaussian elimination to take care of this, just to be sure I'm not tricking myself in terms of, I don't know, Gaussian elimination is nice because, again, it comes to a unique result where the interpretation is unambiguous. So row 2 minus 3 row 1, right? What do we get? We get 1, 1, minus 1, 0. 6 minus 3 is 3. Oh, yeah. Sorry. And then how about a 9? That last column is easy. It stays 0. And then, let's see here. This is row 2 divided by 3. Oh, here. You know what? I'm actually going to do a fraction for once in my life. Check it out. So row 1 minus 1/3. Row 2. I can do fractions. See, you may have thought that I wasn't capable of it. I just try to resist it. So, what's 1/3 of 9? 3. So we're minus 4, right? And if I must be a slave to, the method, this is row 2 divided by 3. I'm doing that just so I can tell you that this is the reduced row echelon form. Of course, do I really need to make this last step to get to a system of equations I completely understand? Not really. I mean, once up to here, it's unambiguous what the solution set looks like. You know the difference? So like here, this next to last step, my second row gives me the equation 3b plus 9c equals to 0. Over here, I have the much improved b plus 3c equals to 0. But I do like the finishing step, just for the sake of being able to tell you the very reassuring fact that this is the reduced row echelon form of the augmented coefficient matrix here, right? Which I better come up with, say m, 0. It would probably be bad form to use a for the coefficient matrix here, right? Since we've used a for a variable. Yeah. But with that, what would that say? That says what? What is this? What's this? What do we learn? If you'll allow me to snake my way back up here. We have learned that a, watch this, is equal to 4c. And we've learned that b is equal to minus 3c. Notice the change in signs, because I changed from, like this equation, b plus 3c is equal to 0, to b equals to minus 3c. So my normal ABC, what's the form of it? It's going to be 4C minus 3C, C, right? In other words, C times 4 minus 3, 1. Any normal has that form for my made-up example. Now, for those of you who have or are taking Calculus 3, how would you do this problem?
Cross product.
Yeah, you take the cross product, right? You find the vector that goes from here to here, you find the vector that goes from there to there, and then you take PQ cross PR, right? And that will give you the cross product. So this should be proportional to the cross product. Just as a check on my algebra, what's the vector PQ equal to? Three, 6, 6. Whew. All right, moment of truth. Is the dot product of this and that 0? If it's not, we're in trouble.
Yeah.
Yeah, 12 minus 18 plus 6 is 0. Those of you who have not had Calculus 3, this does not matter to you. You have a completely algebraic method to do this. You don't need to know the cross product. You can do it with just algebra. So anyway, don't worry about my algebra. Oh, by the way, did you notice something here? This was what is called a remember we called this a homogeneous system? Star and star star, homogeneous system, right? Did you notice what happened with the augmented coefficient matrix for the homogeneous system? You had a homogeneous zeros, 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 zeros. So clearly we could find the solution to a homogeneous system without even writing the column for the inhomogeneous term. Because the inhomogeneous term is 0, and it just stays 0. No matter what row operations you do, you notice that Gaussian elimination works column by column. Like what happens in the Gaussian elimination happens column by column. In fact, you know what I could do? And this is an irreparable modification, so you need to watch me do it because I can't undo it. But you know, this is there you go. True. Because it goes column by column. What happens in Gaussian elimination goes left to right. And so if I add things onto it, it doesn't change what happens to the first two. In retrospect, that means you could go back to the start of this lecture, and those two examples I did, I showed you how they related to what? 4 equations and 3 unknowns, and 5 equations and 2 unknowns. We could also look at those as 5 equations and 3 unknowns, homogeneous, or 4 equations and 4 unknowns, homogeneous, where we just omitted the last column. Right. In fact, there are still more interpretations. A given row reduction has many different interpretations for different related systems. Mission 2 tries to teach you this. So, you guys had other questions, I'm sure? Does that help with, that should help with 14, obviously. And really, 15 is much the same, right? Just plug those points into the equation symbolically. And since A, B, and C are like A, B, and C are playing the role that X, Y, and Z do in our other problems, right? They're the variables. They're what we don't know. So here the X and the Y are actually given. That's the kind of funny thing, right? X and Y are not the variables in these problems. They're the givens. And then A and B and C are the things we're trying to figure out in problem 14 and 15. So I guess the tables have turned there a little bit, right? Yeah. I will tell you this, by the way, in terms of the transpose, there's no particularly nice thing I can tell you. Like the last problem, as you calculate the matrix, the Gaussian elimination and the elimination of its transpose. There's nothing especially nice relating those two. I mean, I can tell you there's one thing I can tell you. We'll work out eventually that if you do the Gaussian elimination of a matrix, and I mean, if you do the row reduction of a matrix, and you do the row reduction of its transpose, you'll end up getting the same number of pivots. this will prove eventually. The number of pivots is the same for the matrix and its transposed row reduction. Yeah.
But for right now, you're basically saying that's two problems. This row
Yeah.
reducing and the row reducing.
Yeah, yeah. It's not just you just, I wish that you just do it and they, oh, transpose. No, it's not that. It's just two separate problems. Masquerading is one problem. So you were asking about the column by column proof?
Yeah.
So again, ever popular question. Let's see here. So you're supposed to show that AB, right, is equal to well, let me. You're supposed to show AB is equal to AB1, AB2, ABP, where B is what? B1, B2, BP, right? So this is a what by what? I mean, what were the size of the matrices involved? N by P? So this is N by P? Oh, and A is M by N? Okay. So we've got M by N by P. That makes sense. Okay. All right. Let me just put it up here. That's N by N. I'm writing that down mostly so I don't write something that's not true. That really has not so much to do with how to do this problem, though. So to show these two things are equal, right, you have options. You could show that each row matches. That seems like a bad choice. You could show each column matches. That's probably a good choice. You could show each component matches. That's what I'm typically selling you guys on. So to show these two things are equal, it suffices to show that A, B, Ij is equal to this thing, right? Now, by the definition of matrix multiplication, what's this equal to? We said that that's equal to the sum. K equals 1 over the interior. So in this case, it's over n, right? K equals 1 to n of A, I, K, B, K, J. That was the definition of matrix multiplication. That's essentially a formula for the dot product of the ith row of A with the jth column of B. All right? So what you want to do is try to meet in the middle. You want to work on the other side until you get to this. That's to me, that's probably the easiest way for you guys to see it. So let's start. I've told many of you this, so I guess I'll tell the rest of you. What's the jth? So this is, I is what? Row index? J is column, right? So what does that mean? That is the ith component of the jth column, right? What is the jth column? First column, right? Here's the second column. What's the jth column? By construction. It's what? ABJ, right? Not just B, ABJ, right? Now, I should really erase this equal. I mean, there's something I'm missing here in my notation, which is very important, and this is not part of it. I mean, your solution, right? This should not be in the start of your solution. That's nonsense. That would be assuming the point, right? So to be clear about my work here, I'm saying that this is the question, right?